Alrighty, today what we're looking at is vertical dilations of functions. So what we have looked at so far is translations, vertical and horizontal, and we've also looked at reflections in the axes. Today we're looking at dilations, and vertical to be exact. Tomorrow we'll look at horizontal dilations, and then on Friday we'll put it all together and look at combined. So a dilation is something that stretches the curve or it shrinks the function, changing its shape and size. So vertical dilation stretches or enlarges or shrinks and reduces the graph up or down, away from or towards the x-axis. We have to notice that we use the letter K for vertical dilation. Shh, girls. We use the letter K for vertical dilation, and that K stretches or shrinks the graph vertically up or down from the x-axis, okay? Or we can also say that it's along the y-axis, okay, and it changes its shape. The value of the parameter K controls the amount of stretching or shrinking. We call K the dilation factor or the scale factor. So for our curve y equals f of x, we have y equals k f of x, dilates the curve vertically. Okay, what we have is this is the same as replacing y with y on k in our y equals fx function. So if k is greater than 1, then the graph is stretched or expanded away from the x-axis, meaning that it makes it taller and skinnier. Okay, if 0 is less than k is less than 1, the graph is shrunk or reduced towards the x-axis, making it wider. Okay, so if it's k is less than 1, it makes it thinner. And then if it is if it's a decimal or a fraction, it makes it wide. Okay, so thin or wide. And it changes the y value of our function by multiplying it. So we've already looked at a couple of our dilations, previous exercises and in previous topics. We're just formalising it now. So we have the function y equals x to the power of 7 is dilated vertically by a factor of 3. We want to find the equation of the transformed function. So what we have is y equals k f of x, and this is where our k value is equal to 3. So that means we're therefore going to have the transformed function is y equals 3, where our f of x is our x to the power of 7. Okay, so we replace our k value with our 3, and we have that our f of x is equal to x to the power of 7 for this function. Okay, our next, so that's pretty straightforward. We're just multiplying our function by 3, putting a 3 out the front. Now, our next example, we want to describe how the function f of x equals log base 2 of x over 2 is related to the function f of x log base 2 of x. So if we look at our function f of x equals log base 2 of x over 2, what is a coefficient that we can pull out the front that would multiply log base 2 of x? A half, right? Because when we divide something by 2, it's the same as timesing it by a half. So this is really just equal to log base 2 of x. So what we have is our scale factor, which we can also call our dilation factor, is going to be that k equals a half, okay, because our half is out the front. And what we do to explain this is we say that f of x equals log base 2 of x is vertically dilated by a scale factor of a half to get f of x equals log base 2 of x divided by 2. Does that make sense? Okay, so whatever our value out the front is of our function, so in this case, our value at the front is our half, that's our scale factor, and that's what we've vertically dilated our parent function by. Okay, as we do more examples, this will hopefully start to sink in, and this is the easier dilation. Vertical is easy, horizontal not so easy. It just doesn't make as much general sense. So example 3, we want to find the scale factor of each dilation of a basic function and state whether the dilation stretches or shrinks the graph. So what we have for our first one here is we have y equals 7x squared. So we need to state whether it stretches, or find the factor is the first bit. Sorry, I missed that. So our scale factor is 7, right? So our scale factor is equal to 7 because we have this in the form of y equals k and then our function. Okay, and in this case, our function is x squared. So what we have is we need to look at our terminology up above. So if k is greater than 1, it is stretched. Okay, so we're going to have that it stretches. So therefore, as k is greater than 1, we have that it stretches the graph. We can just write stretches. Okay. With our next one, right, so this is in the form y equals e to the x on 5. We have that it's y equals k of our function. So k of f of x. What is our function in this case? Our function in B is e to the x, right? So what's our scale factor going to be? A fifth. So scale factor equals 1 over 5, okay? Because we can pull our fifth out the front. So what we have is that, is a fifth greater than 1? No, so as 0 is less than k is less than 1, so that means that k is between 0 and 1, we have that it shrinks the graph. I believe is the words? Yes, shrunk or reduced, so shrinks. Okay, so it makes it, shrinks it away. All right, next page. So it makes it like tiny. Does that make sense? Instead of making it big. So about the y-axis, like it either stretches it along the y-axis. So the first one, y equals 7x squared, stretches it. But then the next one, because the scale factor's a fifth, it like flattens it out more. Does that make sense? Yeah, that's the words they use. You can use the word compressed, reduced. This question just asks about stretches or shrinks, so we'll use that terminology. So we're not moving it, we're just like, so like if this, I'm a parabola, right? So this is y equals x squared, y equals 7x squared is like this, right? Y equals a fifth x squared is like this. Does that make sense? But we're not going up and down, right? That's translations. Right? Dilations is just like skinny, wide. Does that make sense? Okay, next page. Does anyone else have any questions? Okay, the next question. We have the point, so this is on the next page. N is negative 1, 8. It lies on our function. And we want to find the image of n on the function if we have y equals k f of x. So we're going to find the image if we have y equals k f of x. So our k value in our first one is 5. So that means we'll have y equals 5 f of x. Now, what do we affect our y values or our x values when we're doing vertical dilation? Y values. So our point that we've been given is n is negative 1, 8. So to get to our image point, our image is going to be n, and then it's going to be negative 1, and then what we do to our y value is we multiply it by our K value. So then we get that our image, so therefore we have that our image N is negative 140. So if you need a little note, multiply Y by K. Oh, Phoebe's not here. What happened to her? Oh, she's gone home sick. Okay, the next one, we have K equals a half. Shout out to Phoebe on the video too, I suppose. So we'll have Y equals, what's our K value? A half of f of x. All right, so the same thing, we have our point is n minus 1, 8. So to get to our image, we have that n is negative 1, 8, but we multiply our y value by a half. So therefore, we have that n is negative 1, 4, because of half of 8 is 4. Does that make sense? That's pretty straightforward, hopefully. Sorry about all the colours. Okay. Our next example, we have the graph shown is y equals f of x, and we want to sketch the graph of y equals 2f of x. So what we have is our scale factor is 2. Okay, so what we're going to do is we have 3 clear points here. Okay, we are going to multiply the y value of those 3 clear points by 2. So the first one is negative 3, 1. Then we have negative 1, 2. And then we have 1, 1. We sort of have some other points, but they're not as clearly pointed out to us, I suppose. So we do have the x-intercepts, yep, but the x-intercepts aren't going to change because the x-intercepts have a y value of 0, and when we multiply anything by 0, it stays 0. Does that make sense? We can write it down if you'd like. Do you want to do one of them? No, we all get what's going on? Okay, so we'll have minus 3, 1, we'll have minus 1, 2, and we'll have 1, 1. We're going to multiply those y values by 2. Just doing it all at once using the same colour. All right, so that means we're going to get that minus 3, 1 becomes minus 3, 2. We're going to have that minus 1, 2 becomes minus 1, 4. And that 1, 1 becomes 1, 2. So from there, we can pick what colour we're going to graph in. Pink. That's always fun. Okay, I can do green. 3, 2, 3, 2, 3, 2. 3, 2. Minus 1, 4. 1, 2. And that stays the same. Okay, so it's going to be skinnier. Whee, roughly. All right, and then we need arrows at either end. We could put those key coordinates on 1, 1, and then this is y equals 2f of x. How fun's that? Okay. I think we have one example left, is that correct? Like an ABC, maybe?
Yeah,
ABC. Okay, our last one is to do with circles. We love talking about circles, apparently, with our transformations of functions. So example 6, what we have to do is find the equation of the circle x squared plus y squared equals 4 if it's vertically dilated by a scale factor of 3. So for a vertical dilation, what we are going to do is we replace y with y on k. Y on k. Okay, so we have our scale factor equals, what's our scale factor for this one? 3. So our scale factor is 3. So we're going to replace y with y on 3. So what we'll have is x squared plus y on 3 all squared equals 4. So this is x squared plus, when we square a fraction, do we just square the top? No, we square the top and the bottom. So it's x squared plus y squared over 9 equals 4. And what we can do is, that looks a little bit ugly with the over 9, so we can multiply every term by 9. So what that means is this becomes 9x squared plus y squared equals 36. Okay. All right. Part B, I think it's a lot easier if we actually see the circle before doing it. Okay, so with this circle, let's actually sketch it. What we're going to have with our sketch is we're going to have our centre of 0, 0. Okay, what we have is we have our original function, our OG function was x squared plus y squared equals 4, right? So with x squared plus y squared equals 4, it had a centre of 0, 0 and a radius equals 4. Do we all agree with that? Yeah. So, is the radius 4? Have I? 2. Let me down, Betty. Okay, so for this one, its domain and range is both -2 and 2, right? So it also has a domain of -2 to 2 and a range of -2 to 2 for our original function, okay? Now, for our OG function. Now, if we are talking about vertical dilation, are we changing domain or range? Range. So that means that our domain, we can write that in. Our domain is going to still be the -2 to 2. Who was that? Imagine if it came in and started talking. Anyway, so our range is still -2 to 2. What do we think that scale factor of 3 does to our range? So what we have is that our range was, it does make it an oval, Kalana. So our range was -2 to 2, right? What we have to do is we have to multiply our range by our scale factor of 3. So we get that therefore our range is going to be -6 to 6. So if we need a note, multiply range by k. All right? That then helps us, Jaden, to be able to sketch it a little bit. Okay, so finding our domain and range does actually help us. Well, you can do a table of values, but what we have is that we're going to have that our function has a centre of 0, 0. It's going to have, the domain is still going to be -2 to 2, right? So it was a circle, but what's happened is, so we did have a circle that looks like that, right? Nobody draw that. That was our circle. Okay, what's now happened is it's staying the same with these values, but our y values are now going to pop up to be, oh, the line. It looks like an I. To be from -6 to 6. Does that make sense? Cool. So our domain stays the same, but our range goes up to be up there. So this is our 9x squared plus y squared equals 36. And then our blue one was our x squared plus y squared equals 4. Okay? While you're doing that, I'll just read the bottom thing. The bottom thing is what we did yesterday, which was our reflection. So we technically, when we have a reflection of -k, okay, it is also our vertical dilation. But we looked at that yesterday, so I'm not going to talk about that